In 2026, a claim started spreading across YouTube and social media that an AI had finally cracked the deepest secret in mathematics, a hidden pattern buried inside prime numbers, a 500-page proof, a discovery so shocking that researchers supposedly refuse to believe their own screens. It sounds incredible. There's just one problem. It isn't true. No such proof exists. No peer-reviewed paper backs it up. And yet the real story underneath the hoax is stranger and more interesting than the fake version, because it's about how close AI is actually getting to problems humans have failed to solve for 2,000 years, and how easily a true story turns into a false one once it starts traveling. Let's start with the numbers themselves, because you can't understand why this story spreads so easily without understanding what's actually at stake. A prime number is any whole number greater than 1 that can only be divided evenly by itself and by 1. 7 is prime. 12 is not, because it breaks apart into 2 6s or 3 4s. This sounds like a fact for children, and in one sense it is. You can explain it to a 10-year-old in 30 seconds. But primes are also the atoms of arithmetic. Every whole number is built out of them, multiplied together in exactly one way, the way every molecule is built from atoms on the periodic table. And for over 2,000 years, mathematicians have known these atoms exist in infinite supply, but they have never been able to predict exactly where the next one will appear. This isn't just an abstract curiosity locked away in university math departments, either. Prime numbers are the backbone of modern encryption. Every time you send a private message, log into a bank account, or make an online purchase, there's a decent chance the security protecting that transaction relies on the fact that multiplying 2 huge prime numbers together is easy, while reversing the process, taking a giant number, and figuring out which 2 primes were multiplied to make it, is brutally hard for even the fastest computers. That asymmetry is the whole foundation of a lot of internet security. So when someone claims a breakthrough in understanding the hidden structure of primes, it isn't just a math nerd headline. If it were true in the way some viral posts suggest, it would touch cryptography, cybersecurity, and the infrastructure a huge amount of digital life depends on. That's part of why these claims spread so fast. The stakes, if true, would be enormous. That's the part that should stop you. We proved primes go on forever more than 2,000 years ago, using an argument so clean it's still taught to first-year students today. But knowing they never run out is very different from knowing where they show up. Look at the first several primes, and the gaps between them seem to wobble with no rhythm. 2, then 2 again, then 4, then 2, then 4, then 6. Sometimes primes sit right next to each other. Sometimes there's a long, empty stretch with nothing. No formula tells you in advance where the next one will land. You just have to go out and check, one number at a time. And for a field built entirely on the idea that everything has a reason, that every result traces back through an unbroken chain of logic that is deeply uncomfortable, mathematicians don't believe the primes are random. Random would almost be easier to accept. They believe there's a hidden order down there that nobody has ever fully read. The first person to get close was Carl Friedrich Gauss, around the year 1800. As a young man, he became obsessed with counting primes. How many appear below 100, below 1,000, below 10,000? Filling notebook after notebook by candlelight. He found something real. While you can't predict any single prime, you can estimate remarkably well how many primes will appear below any given number, using one elegant formula. It works. It's beautiful. Compare Gauss's prediction against the actual count of primes at any scale, and the 2 lines track each other with almost eerie closeness. But Gauss understood its limit. It was an approximation, not an explanation, like knowing roughly how many raindrops will fall on a field without knowing where any single drop lands. In mathematics, roughly right is not true, and Gauss knew it. The formula described behavior. It didn't reveal a mechanism, and that gap is exactly what would occupy mathematicians for the next century and a half. 50 years later, Bernhard Riemann took a completely different angle. Instead of counting primes from the outside, he built a strange mathematical object now called the Riemann zeta function. In simple terms, a machine that takes in numbers and spits out other numbers, except this machine works on a two-dimensional plane of numbers instead of a single line. Most points you feed into it produce ordinary results. But at certain special points, the output is exactly zero. Riemann started plotting those 0 points, and he noticed something remarkable. Every single one he could calculate lined up on one thin vertical line running through the plane, a line where a particular coordinate, what mathematicians call the real part, equals exactly 1/2. Not scattered, not clustered in some rough band, all on one perfectly straight line. He couldn't prove it would hold forever. He had no argument guaranteeing the next 0, or the one after that, or 1 trillion places further out would land in the same place. He simply had the data in front of him, and he trusted it enough to write it down, not as a theorem, but as a hypothesis, almost in passing, inside a paper about something else entirely. That offhand remark became the Riemann hypothesis, arguably the most famous unsolved problem in mathematics, because those 0 points aren't just decoration. They are mathematically tied to the exact deviations between Gauss's smooth estimate and the real, jagged truth of where primes actually fall. Each 0 contributes a kind of correction, a ripple, and when you add up the ripples from all of them, Gauss's rough approximation snaps into the exact, true count. If every 0 really does sit on that line, the primes have hidden order after all. If even one doesn't, huge portions of modern mathematics built on that assumption would need to be rethought. In the year 2000, the Clay Mathematics Institute put the Riemann hypothesis on a list of 7 Millennium Prize problems, each worth $1 million to whoever solves it. More than 2 decades later, only one of the 7 has ever been solved, and the Riemann hypothesis is not that one. Researchers have since checked the first 10 trillion zeros by computer, and every single one sits exactly where Riemann predicted, without exception. 10 trillion confirmations, and it still isn't proof because mathematics doesn't accept probably. It demands certainty out to infinity, and no amount of checking finite cases can deliver that. This is the gap that AI has actually been stepping into, just not in the way the viral claims describe. Real, verifiable progress has been happening, and it's worth being precise about what it is, because the true version is genuinely impressive on its own. In January 2026, a researcher using GPT 5.2 Pro tackled Erdos problem 281, a question that had been open since 1980, producing an argument that was then formalized and independently checked by other mathematicians. Field's medalist Terence Tao called it one of the clearest cases yet of AI actually solving an open problem, while also cautioning that these were, in his words, the lowest hanging fruit, the kinds of problems solvable with standard techniques already known to specialists. That caveat matters. It's honest. It's the opposite of the hype. Separately, Google DeepMind has built systems, including one based on its Gemini DeepThink models, aimed at competition-level and research-level mathematics, following earlier systems that reached silver medal performance on international mathematical Olympiad problems. DeepMind has also previously used AI to surface genuine, previously unnoticed relationships in knot theory and representation theory, abstract corners of pure math that normally take a decade of training just to enter, findings solid enough to be published in respected journals. None of that is science fiction. It's real, it's documented, and it shows something worth sitting with. These systems, because they don't carry the accumulated assumptions of a 2,000-year-old field, sometimes look in places human intuition quietly tells experts not to bother checking. There's also a more skeptical, technical argument worth knowing about because it pushes back against the entire premise of AI. We'll just find the formula. A 2024 theoretical paper examined the question from the other direction, using tools from algorithmic information theory, and argued that discovering a genuine closed-form formula for the primes through machine learning alone may be fundamentally impossible in principle. Not because current models aren't good enough yet, but because of deep limits on what pattern matching can extract from a sequence as structurally random-looking as the primes. Other researchers who've tested large language models on prime-related benchmarks have found something similar in practice. When pushed to produce formulas for genuinely hard, unsolved sequences, Models sometimes generate outputs that technically match all the known test cases, but don't actually constitute real mathematical breakthroughs, closer to a curve fit than a proof. That doesn't mean AI is useless here. It means the realistic path forward probably looks like what's already happening. Incremental, human-checked, narrowly scoped progress, not a single dramatic reveal. But none of that is a proof of the Riemann hypothesis. None of it is a hidden formula for the primes. And this is where the fake story comes from. Not nowhere, but from real progress that got exaggerated, repackaged, and sent viral. Fact-checkers tracking the claims found that posts throughout 2026 described a quantum AI system producing a 500-page proof revealing a secret pattern behind the primes. No such proof has ever been published or peer-reviewed by any recognized mathematical body, and no credible institution. Not DeepMind, not the Clay Mathematics Institute, not any university math department, has confirmed anything close to it. It traces back, in part, to a chain of similar hoaxes, including a well-known 2024 joke by an AI researcher claiming a model had proved the Riemann hypothesis and been shut down for being a danger to humanity, a claim its own author admitted was a joke within hours of posting it. Colleagues even leaned into the bit afterward, piling on with increasingly absurd follow-ups, the way an inside joke escalates once everyone realizes it's landing. The joke never fully died, though. It kept getting reposted as if it were real, each time picking up a little more borrowed credibility from actual, unrelated AI math breakthroughs happening at the same time. The Erdos problem, the Olympiad results, the knot theory paper. Put those genuine milestones next to a screenshot of the old joke, strip away the context and the dates, and you get something that reads as one continuous story of AI conquering mathematics, when in reality it's several unrelated threads stitched together by whoever benefits from the engagement. There's even a prediction market that opened on whether AI will resolve the Riemann hypothesis by 2035, sitting in the low 40% as of mid-2026, which tells you something interesting on its own. That number isn't pricing in an imminent solution. It's pricing in 9 years of continued, gradual acceleration in AI-assisted mathematics, layered on top of a noisy background of exactly the kind of recurring hoaxes we've been talking about. Traders chasing the headline often move the number even when nothing underneath it has actually changed. It's worth asking why this particular hoax works so well, because the answer says something about how we think, not just about how misinformation spreads. The Riemann hypothesis is famous specifically because it's unsolved, because $1 million sits on the table for anyone who cracks it, because some of the greatest minds in history have stared at it and failed. A story that says an AI finally solved it plugs directly into a narrative we already find compelling. The idea of a machine seeing what humans, blinded by our own expertise, cannot. And there's a kernel of truth buried in that narrative, which is exactly why it's so easy to believe. AI systems really have found genuine mathematical relationships that trained specialists missed, not because the AI is smarter in some general sense, but because it doesn't carry the same inherited assumptions about where the interesting structure is supposed to live. A human mathematician arrives at the primes with 2,000 years of theory on their shoulders. A gift because it focuses attention, but also a cost because every framework that tells you where to look is quietly telling you where not to look. A trained system built without that specific inheritance can sometimes wander into the places human intuition has learned to avoid. That part is real. It's just a much smaller, much more careful claim than AI solved the unsolvable problem. And small, careful claims don't go viral nearly as fast as dramatic false ones. So what should you actually take away from all this? First, that the real relationship between AI and the deepest problems in mathematics is progressing, but slowly, incrementally, and with real mathematicians checking every step, not through some single dramatic breakthrough announced in a thumbnail. Second, that when you see a claim this big, AI solves 2,000-year-old mystery, hidden pattern found, proof that shocked researchers, the responsible move is to ask where the peer review is, not to assume the silence means the establishment is covering something up. Extraordinary claims in mathematics get extraordinary scrutiny because, unlike almost anywhere else, math has a built-in mechanism for catching liars. A proof either holds up under checking or it doesn't, and there's no room to fudge it. Third, and maybe most important, the true story doesn't need exaggeration to be worth telling. Real AI systems are genuinely starting to touch problems that have resisted human minds for centuries. That's remarkable on its own. It doesn't need a fake 500-page proof to be interesting. The Riemann hypothesis is still sitting exactly where Riemann left it in 1859, and proven, heavily evidenced, and completely open. 10 trillion zeros checked, everyone on the line, and still not a certainty. Somewhere out past everything any computer has ever reached, there could be a single rogue zero waiting to break everything. Or there could be nothing but orders stretching to infinity, exactly as Riemann guessed. Nobody knows yet. Not Gauss, not Riemann, not the mathematicians alive today, and not any AI system that exists right now, no matter what the thumbnails tell you. What we do know is that the tools trying to answer that question are getting sharper every year, and that the next real breakthrough, when it comes, is going to look a lot less dramatic and a lot more careful than the version that goes viral. So here's the honest question worth sitting with. Not did AI already solve this, because it didn't, but what happens to how we trust information in math and everywhere else when a well-told fake story travels faster than the true one ever could? Tell me in the comments what you think the real turning point will look like when it finally happens.